All right, folks, this is styrofoam in that same aquarium. And you can see if I do a very similar thing that I did to the zucchini, you can look right at the surface level of the water and you can tell, boy, there's not a lot of that styrofoam below the surface of the water. By far, the majority of it is above water. And so what I'm going to do is get that percentage based on what we already know. If you remember, that's the same piece of styrofoam I used in the density and pressure one. That small styrofoam had 4.82 grams. There's the length, width, and height. There's the density. Or I'm sorry, there's the volume. The density in grams per cubic centimeter was 0.0123. The density in kilograms per cubic meter is 12-ish. All right? Now, you remember the density of H2O, right? That's 1,000. And the density of this is 12.3. So if I kind of round that 12-ish, I'll maybe just call it 10. Would you agree that this is about 10-ish relative to 1,000, which is the density of the water? So if the density of this styrofoam is 10-ish, the density of that water is 1,000-ish. That means this is 100 times more dense than that, right? And if I take 10, the density of this, and divide it by 1,000, the density of that, I will get 0.01, which is the gravity of styrofoam. It's 1/100th the density of water. What the gravity then tells you is the amount of this stuff that's below the surface compared to above it. So if this is 1/100th as dense as water, then what I would expect is the volume of styrofoam that is below the surface is 1/100th of the volume of the styrofoam that is above the surface. So 1/100th of the total, 0.01 of the volume is below the surface. 0.99 of the volume is above the surface. And what I'll do now is some math to kind of confirm that, and we will see what the total volume of that is and what the gravity is. And we can do the math based on this drawing, which is one I would like for you guys to be able to do, where this is what I mean when I say treat it like a Newton's second law problem, because this is a Newton's second law problem. What we're going to do is calculate the buoyant force. We're going to get the volume that is submerged, okay, the V submerged out of this. All right, I don't know, it'll take a second to find itself, but it should focus here in a bit. Remember, the force of gravity is equal to mg. The buoyant force is equal to rho of the liquid, the water, times g, times the volume that is submerged, okay? That's what it's equal to, rho g v submerged. All right? Since this item is floating, it's obviously in equilibrium. It's not moving. That means these two equations, those two formulas are equal. If I sum the forces in the y, it will equal mass times acceleration in the y. May, since the acceleration is 0, may goes away. So the upward force, FB, minus the downward force, FG, equals the number of days I went to school this year. 0. Which means these two are equal to each other. So it will be the buoyant force is equal to the force of gravity. This is the mass of the styrofoam times G. This is the rho of H2O times G times the V sub. Okay? You can tell that it doesn't matter what planet we're on. What I will do to isolate V sub, the amount of volume that is submerged, it's the mass of the styrofoam divided by the density of the H2O. Okay, the mass of the styrofoam is what we measured in our last video. It is 4.82 grams. Now, what I'm going to do with that is turn it into kgs. 4.82 grams is 4.82 e negative 3 kgs. I need to do that because this density of water is 1,000. That's kgs per cubic meter, okay? And that'll kill the kgs. So this is already E negative 3, the volume that is submerged. You can do this in your head. You don't need a magic box. It's 4.82 divided by 1,000, which means it's 4.82 with this E negative 3 to another E negative 3. So it's 4.82 E negative 6. That's cubic meters. Okay? That's the amount of that styrofoam that's below the surface. It's obviously not a lot. What I'm going to do is put that number in terms of the volume that we already know of that small styrofoam, 391. Now that's cubic centimeters. So for me to turn this from cubic meters again into cubic centimeters, just to make it somewhat comparable, what I'm going to do is that same conversion. The V sub, the volume that is submerged, is equal to 4.82 E negative 6 cubic meters. I'm going to say, okay, cubic meters into cubic centimeters. All right? You all know there are 100 centimeters in 1 meter. Okay? An easy thing to do is forget that that cube applies to everything in there. So sometimes people write this type of conversion. I'll get rid of those cubes and just say there's 100 centimeters in a meter. Sometimes people write that cube up there, remembering that it applies to everything. All right? So if I apply this cube to the cubic centimeter, that's cubic centimeters. Apply that cube to the meter, that's cubic meters. That's what will kill this. And I have to move the decimal point, if you remember, 6 places, because it's times 100 3 times. So 100 times 100 times 100. This conversion then is 4.82. Instead of it being E negative 6, I'm going to move the decimal point 6 places, and that means E to the 0, which means it's just like that. 4.82 cubic centimeters is the volume that is below the surface. Now, compare that to the total. I said it's going to be about 1/100th of the total, right? Well, you remember the total is 3.91. That's what we measured, calculated the other day. So that's 400-ish, ain't it? And that's 4-ish, ain't it? So the ratio of the amount that is below the surface compared to above the surface, V sub compared to V total, 4.82 cm3s divided by 391 cm3s, and you'll get a percentage, and it's going to be dancing around 0.01. I mean, 4.82 divided by 391 is 0.0123. All right. So ish 1.23% of that styrofoam is below the surface, and 99-ish% of it is above. So that agrees with what our ish estimate was. Now, what we're going to do with that is a little bit of math. Let's say, well, when you see that item floating right there, do you see something awfully similar to a boat? So it's a piece of styrofoam in an aquarium. That means it's going to be awfully similar to a boat. And this is just one of those little tangerine cutie type things I happen to have in my kitchen here. What I'm going to do is place this item on that styrofoam and hopefully not topple the styrofoam. Okay, there it is. Good. I like it. Can you tell now that more of the styrofoam is below the surface, right? It's sunk a little, which should make sense because I've added some mass to it. And can you tell I can progressively add more and more of those little tangerine things? And eventually that styrofoam will end up having its top surface level with the surface of the aquarium water. And when that happens, I can no longer put little tiny oranges on top of the styrofoam and keep it floating. It will once again sink. So the purpose of this particular activity, which I refer to as the Life Raft, is let's pretend in our headsies that this piece of styrofoam is a life raft. This orange are people who are trying to cling to the life raft and make it stay afloat. There's a maximum capacity, meaning the maximum number of oranges that item can support and stay afloat. And that's what I'm going to demonstrate to you guys how to calculate, okay? And then you are going to do it as a virtual activity. All right, so what we're going to do now is shift gears, and we're going to say, let's pretend in our headsies that this is that piece of styrofoam, and the water level is now level with the top. Therefore, the V that is submerged is 100% of the volume of the styrofoam. And these are the various number, however many there are, of those oranges. I don't even know. I didn't do the math yet. We'll learn together. But how many of those oranges can I stack on top of that styrofoam to get it to where the surface of the water is level with the top of the styrofoam? That's the maximum number of occupants, if you will, in that life raft. Hopefully you can tell it's still just two arrows, an up and a down force, a buoyancy and a gravity. The difference is that V sub now is no longer what we're solving for. We know the volume that is submerged. It's the total volume of the styrofoam. Okay? What we will then find out is what is the maximus mass it can support. Okay? That's what we're going to do. These oranges contribute to total mass, but they do not contribute to the buoyancy, because the only thing that contributes to the buoyancy is the water that is pushed out of the way by the styrofoam. All right, so there's still only two arrows, FG and FB. They are still equal to each other because this item in the aquarium is still in equilibrium. It's not sinking, it's not floating, it's still in equilibrium. So it's still like life, it adds up to nothing. These two arrows are still the same. So the FG equals FB. All right. Remember that it's the same setup that we did before. Sum of the forces in the y equals MAY. Buoyancy minus gravity equals the number of days I've been to school, so buoyancy equals gravity. I just went here. Okay? So the next thing I'm going to do is replace those two. I have the mass of the whole thing times gravity, the mass of the whole system. Okay? The planet Earth, this planet Earth exerting this gravitational force, the planet Earth is stupid. It doesn't know it's styrofoam plus oranges. It just thinks it's one item that it's tugging on. So the planet Earth has no clue that that gravitational force is made up of the whole entire system, or that it's not just one item. So I just the mass whole times g. The buoyant force, the water that has been pushed out of the way. The water is stupid too. It doesn't know that it was pushed out of the way by styrofoam and oranges. It just knows something pushed it out of the way. And the amount of water it pushed out of the way is the maximum amount of water this piece of styrofoam can push. The maximum amount it can push is its total volume. It can't push any more water out of the way than its own size. And I said the volume of the styrofoam. Okay, the volume of the styrofoam, that's what that is, the whole entire volume. You can tell again, it doesn't matter what planet we're on, the mass that this guy can support is equal to the density of the water times the volume of the entire object. All right, the only difference is I will get it so that it is in the same units. So the mass of the whole item is the density of H2O, which you guys all know is 1,000 kilograms per cubic meter. I'm going to multiply that by the volume of the small styrofoam. Remember, it is 391, but that's cubic centimeters. 391. Now, that's cubic centimeters. Remember how to go from cubic centimeters into cubic meters. There are 10 to the 6th different decimal places, okay? It's like this up here. It was 100 cubed to go from meters into centimeters. It's 100 centimeters in a cubic meter. It's 100 cubed cubic meters in a cubic centimeter. So it's 100 3 times. That's 6 decimal places, 6 spots, 2 zeros 3 times, 2 zeros 3 times. So I am going to multiply this by 10 to the 6th, E6 cubic meters. Now, is that 6 going to be a positive 6 or a negative 6? Meaning, do I want a really big exponent to go from cubic centimeters into meters, or a really small exponent? And the answer is small. All right, E negative 6 cubic meters. So the mass of the whole system, the maximus mass that styrofoam can hold up is literally equal to the weight of the water, or the mass, I should say, of the water that it pushes out of the way. All right, so I'm going to take, and this is something very easy you can do in your head too. I'm going to take this number, 391 times 10 to the negative 6, and I'm just going to multiply it by 1,000. All right, that's all I'm going to do. The cubic meters die. I'm left in kilograms. That'll be a number of mass, or an amount of mass. 391e negative 6 times 1,000. Well, that's going to move this decimal 3 spots. This will be 391e negative 3 kilograms, okay, which is 0.391 kgs, which, if you want to go in grams, is the same thing as 391 grams. It's up to you. We'll probably keep everything in kgs, but that's the total amount of mass it can hold up. All right? Now, total mass the styrofoam can support. Due to the maximus buoyance force, the maximum force of buoyancy, because again, the only place buoyancy comes from is from the styrofoam pushing water out of the way. Once it pushes the total amount of water out of the way that is its own volume, it can't push any more water, right? So the max support, equals 391 grams. From that, I'm going to subtract the mass of the styrofoam itself, which is not a lot. Remember the other day, we measured the mass of the small styrofoam. It's 4.82 grams. So all I'm going to do is subtract 4.82, 391 minus 5-ish is what, 386? So a little over 386. 386-ish grams. Okay? That's the maximum amount of mass in addition to itself that styrofoam can hold. So how many oranges is that? Well, I don't know. The next thing I got to do is get the mass of an orange, or one of these little oranges, whatever the hell you want to call them. I don't care. Tangerines, cuties, little guys, whatever. Little guy oranges. Okay, I'm going to take these guys out of here. I'm going to move the scale here. Hopefully the camera stays nice, because sometimes when I move the camera, it doesn't like it. Okay, I just put that on the scale. You can see it says 76.31 grams. That's the mass of the orange, 76.31 grams. Okay, so what I just did was I wrote that right there, the mass of an orange, 76.31 grams. Okay, 76.31. Well, the most it can hold is 386. Each individual is 76-ish. So if I want to know the maximum number of oranges it can support, all I got to do is push the divide button. 386 divided by 76. If you want to put the 0.31 in there, you can. I kind of ished that anyway. It doesn't really matter. 386 divided by 76.31. And I'm looking at 5-ish, right at 5-ish. So that piece of styrofoam in the aquarium there, if I put one orange on it, it'll sink. Put 2 oranges, it'll sink deeper. Put 3 oranges, it'll sink even deeper. 4 oranges, it'll sink even deeper. And when I put the 5th orange on there is when the surface of the water will be right at the surface of the top of the styrofoam, right there-ish, okay? That would take 5 oranges. Cool? Okay? That's the maximus capacity, because if it goes any deeper, you're now below the surface, and that's what we call, you're no longer adding to the buoyancy. You can't. Okay? So, what you guys are going to do is the exact same activity that I just demonstrated. But you're not going to use styrofoam because I just did. So I'm going to get rid of the styrofoam. And I'm going to have you guys use one of 2 different objects. And that object will depend upon what chair you happen to be sitting in. This is just the lid from a little plastic container of rice. Gluten-free, so if you're sensitive to gluten, you can use this one. This is the lid to a Petri dish that I swiped from the Mullinator. Don't tell her. I'm going to use the lid in both examples. These are going to be your boats. So that sucker floats like that. That's easy. This sucker floats like that. That's easy, right? What you need to know then is the mass of these guys, all right? If you're sitting in an odd numbered chair, you will be using this, all right? If you're sitting in an odd numbered chair. So I will say the lid to the rice is for folks sitting in an odd numbered chair. If you're sitting in an even numbered chair, then you guys will be using the lid to a Petri dish as a life raft. Okay? So, what we will do is write down the mass of these individual guys, okay? This red lid has a mass of 12.19. You're going to want to write that down. That's the mass of the red lid. Those of you using the Petri dish lid, you're going to want to write that down. 3.53 grams. Okay? Now, the folks using the rice lid, I'm going to zero this. Your equivalent to oranges will be this hex nut here. That has a mass of 16.59. So those of you using this will be using this. Okay? So this naturally gluten-free rice, whatever, that lid, you will be placing these guys in. Each one of those has a mass of 16.57. Your job will be to tell me how many of those can this hold, how many of those can this hold without sinking. Okay? Those of you using this item, which you already wrote that mass down, right? 0.34. You will be using pennies as your occupants to the life raft. These pennies, when I put on the scale, have a mass of 2.49, right at 2.5-ish grams. So your job is to tell me how many of these one of these can support. All right? And so literally what you're doing is what I just did with the styrofoam. So you'll need to know the maximum amount of water these guys can displace, okay? So I'm going to give you the diameter of this, which you can say is right around 6 centimeters. That's the diameter of the Petri dish. And the depth of that Petri dish is right around, if you can't read it, I'll read it to you. It's dancing around 7-ish millimeters. Okay. So 6-ish centimeters, 7-ish millimeters. Okay. That's for folks using this. So with that, you can calculate the maximum volume of water. If I push this down, it keeps pushing water out of the way, out of the way, out of the way. Once it's completely submerged, boom, that's when it takes on its own water and starts to sink. Okay, so the maximum amount of water it can push out of the way is when its own volume is submerged. Okay, folks using this, those in odd numbered seats, again, are using this. Folks in even numbered seats are using the Petri dish. So if you're in an odd numbered seat, this is what? A little over 9 centimeters in diameter. I'm going to call it 9.2. That'll make it easy to divide. 9.2. Okay, 9 point. Yeah, it's all right. 9.2 centimeters. That'll make it easy to cut in half. The depth of this looks like it's right at, what, 1.5 centimeters. I'll call it 15 millimeters. All right. So what you'll be doing again is figuring out what's the maximum amount of water it can push out of the way. And then as I keep adding these, you can tell this is going to sink a little deeper. And I'll keep adding these until they sink even deeper. And you got to be careful when you add these because, oof, you can see how the thing starts to tilt a little bit. But every time I add one, you can tell more of it goes below the surface, right? It's going below the surface. And how many of those can it sink? So you're doing the exact same math I just did. All right. So please realize this is a virtual activity. It's called the Life Raft. I just did sample math using styrofoam and oranges, but you guys will do the exact same math using either the lid of a Petri dish and pennies or the red lid to a can of rice, but using those nuts that are these guys for that have, what, 16-ish grams a piece. So how many of those can it hold? How many of those pennies? That's the Life Raft. Yay, physics.